Greetings, chemists. Today we're going to continue our series on acids and bases with the topic of pH. And let's start with water, just pure water. So you have a beaker, all you've got in there is some H2O. If you were to look into that beaker, all we know water molecules look something like this. And I'll draw a couple of them. It turns out, we talked last time about how an acid is a substance that will donate a proton to a water molecule, and a base is something that will accept the proton from a water molecule, or steal a proton, or take a proton from a water molecule. It turns out that pure water actually behaves a little bit like an acid and a little bit like a base, and I'll show you what I mean. If you would have had a bunch of pure water molecules bouncing around inside of a container of water, they bounce into each other, and sometimes you can get the following reaction. One of the water molecules, the lone pair, will kind of attach to that hydrogen, and the hydrogen will leave behind its electron, so this pair of electrons will stay on this oxygen. And what you're left with at the end of it is a hydroxide molecule and a hydronium molecule. Like that. Now, and this would be an acid-base reaction. If you were to write this out as an equation, you would say that two water molecules, two H2Os, go towards an OH minus and an H3O plus. And in this case, one of them is sort of acting as the base, and one of them is sort of acting as the acid. This is sometimes called the autoionization of water, because it spontaneously does this. Now, it is an equilibrium situation, because anytime you have H3O plus and OH minus, they do react with each other to go backwards and form H2O. And in fact, the equilibrium is heavily favored in the left direction, the direction of water. But it does happen to a certain extent. So if you look at the equilibrium concentration of these, it happens to be very small. But water is technically both an acid and a base in this case. Side note, something that can act as both an acid or a base is what we call amphoteric. Amphoteric, I can spell. Or sometimes I've heard it called amphiprotic. Ampho, if you remember, like an amphibian can live in land or water. It has both characteristics. It's just like this. Water can have both characteristics of an acid and a base. So let's look inside here. At any given point in a glass of water, you have mostly water molecules, and occasionally, not occasionally, you have some H3O pluses and some OH minuses. How many? Well, we can calculate the concentration in a glass of water. It happens to be pretty well documented that the concentration of H plus ions is equal to the concentration of I say H plus, that's the H3O plus ions, and the concentration of OH minus ions, they're the same, and it's about 1 times 10 to the minus 7 molar. Which is very small. To put that as a decimal, 1 times 10 to the minus 7 molar is 1, 2, 3, 4, 5, 6. Right there, molar. So very, very, very small concentration of hydronium, and a very small concentration of hydroxide. Let's talk about some things. So let's suppose that into a glass of water I add, so this used to be pure water, and I'm going to add a little bit of HCl. Not much, a tiny amount. In fact, when I add the HCl to water, what I'm actually going to be doing is adding more H plus ions. So the HCl, we know HCl plus water will go into H3O plus Cl minus, right? We're making more H3O plus, more hydronium. And let's suppose that if pure water is 10 to the minus 7th molar, I add just a little bit of HCl to the point that the new concentration of H3O plus, now, after adding the HCl, is 10 to the minus 6 molar, or 0.23. There. So I have one less zero, essentially. Still a very tiny concentration. You wouldn't even probably taste it, but it would be different. It would be 10 times more concentrated, right? From 10 to the minus 7 to 10 to the minus 6 is multiplying by a factor of 10. Okay? That would go up. And I could add a little bit more. Let's suppose I keep dumping this in. I could go to 10 to the minus 5 molar, which again would be 1, 2, 3, 4, 5. That much, which again is very small, but we're increasing. And then I go up a little bit more, right? You can keep going. What we're talking about is increasing the concentration of this hydronium ion by 10 times, right? So if I had pure water, a 10 to the minus 6 molar is 10 times stronger than pure water. A 10 to the minus 5 molar is 10 times stronger than this, or 100 times stronger than pure water. So chemists got together and said, hey, let's start describing acid concentration like this, 10 to the minus 6, 10 to the minus 5, 10 to the minus 4, in terms of how many powers of 10 stronger than water it is. Well, this gets a little cumbersome, right, having to write this out each time. So they came up with the pH system, and they said, here, what we're talking about is how many hydronium ions, how many H pluses, how many hydrogens we added to the water to make it 10 times stronger. And let's say that we'll use this number here. So when we have a concentration of hydronium ion that's 10 to the minus 6, we're going to call that pH 6. And when we have it 10 to the minus 4, we'll call that pH 4. The pH stands for power of hydrogen because this was an exponent, right? We got power. That was their nomenclature. So let's talk about some things you may be familiar with. Okay. I'm just going to look here. So this 10 to the minus 6, this is a very, very kind of weak acid solution. It's just that almost nothing. Like pure water is only 10 times weaker than this. This is only 10 times stronger than pure water. Things like milk. Let me start a new page here so I have room. So like pH 7, that's pure water. That's 10 to the minus 7 molar. Okay. And let's go to pH 6, which is just 10 times stronger than water, or 10 to the minus 6 molar. That would be like milk. Milk has lactic acid in it, which adds a little bit of extra hydrogen to water, but not much. All right. When you go to pH 5, you're talking coffee. Coffee maybe is 100 times more acidic than pure water. People drink it all the time, and I don't think it's the acid content that does much to them. But coffee has other effects on your body. We won't get into that. That's a biology question. pH 4, we're getting into the area of like wine. That's 10 to the minus 4 molar. Now that would be 10, 100, that'd be 1,000 times more acidic than pure water. We get down into this area. We're getting close to vinegar. If you let your wine sit too long, it'll actually turn into vinegar. Okay, vinegar, you can actually taste the acid. That tastes pretty sour at that point. And it can do some damage if you were to get it on your skin or in your eyes or something. And around that range as well, 10 to the minus 2 molar, we're getting into like lemon juice. Lemons are very acidic, okay? Sometimes even more sour than vinegar. You can feel that. Okay. If you get down into pH 1, which is 10 to the minus 1 molar, okay, that's like what's in your stomach. Stomach acid is very acidic. What are we at now? 10, 100, 1,000, 10,000, 100,000. So stomach acid is 1,000,000 times more acidic than pure water. You remember, stuff you eat goes down into your stomach, and basically your stomach acid corrodes it. It breaks it down into much different chemicals and more simple molecules. So very dangerous stuff. If you've ever vomited and you've gotten some stomach acid in your throat, it burns, right? Okay, that's because it's a very strong acid at that point. And then like the acid we use in lab. Now you can obviously dilute acids or concentrate acids in the lab, but like 10 to the 0 molar or like 1 molar would be like a pH 0, and that's like a strong HCl solution. So 1 molar acid. We've before we tested a sugar in our lab, we did 1 molar sugar solution. You actually tasted that, and some of you thought it tasted pretty good. Well, that's a certain strength of sugar. If you have the same strength but not sugar molecules, acid molecules, that's 10 times stronger than your stomach acid. That can really do some damage to your skin or your body tissues. Now, what if we go the other direction? So this would be like an acid scale. What if we go the other direction? We go towards basic molecules. Well, water is also, remember we said it has some H3O plus, that's like the acid molecule, but it has some OH minus, that's like a base molecule. And base molecules are similar in function to acid molecules. They could still be dangerous. They could still be corrosive. And they do react with water. So let's look at the other direction. If I went from pH 7, let's start at pH 7 again. Water has 10 to the minus 7 molar OH minus as well as 10 to the minus 7 H3O plus. It has the same concentration. So water is also a very weak base. And again, this amount of hydroxide is about as dangerous as that same amount of H3O plus, the hydronium. So what if I went to 10 to the minus 6 molar hydroxide? In water, what would happen is the concentration of H3O plus multiplied by the concentration of OH minus is always going to be a constant. It never changes. So in pure water, what you have is 10 to the minus 7 times 10 to the minus 7, right? You have the same concentration in both. It's 10 to the minus 7 molar. And so the total concentration, well, you wouldn't say the total concentration, the equilibrium constant, I guess, for water is 10 to the minus 14. So when water, in the previous examples, anytime the H3O plus goes to like 10 to the minus 6, that means we gain, that's 10 times stronger H3O plus. You actually lose some OH minus. You go down to 10 to the minus 8. You get 10 times less OH minus. So this is kind of like a balancing act. They always have to add up to 10 to the 14th. So what if we go the other way? What if we go to 10 to the minus 6 molar hydroxide? That would be 10 times more hydroxide ions than we previously had. Well, if I go to 10 to the minus 6 hydroxide, I'm actually going to go to 10 to the minus 8 hydronium. And that was the basis for our pH scale, was how much hydronium is in the water at that time. So if I went to a stronger basic solution, which is a stronger base, I would get a pH, let's say a pH 8. That's even than water, but it's because it's 10 times more base molecules than water, 10 times more hydroxides than water. Okay, so what does that look like? Well, a pH 8, which is 10 times more hydroxide, a good example of that is something like your blood. I think your blood's like 7.2 or 7.5. Now, this may depend on what you've been eating, but blood is a little bit basic. Okay, and that would be 10 to the minus 6 molar hydroxide, which is technically 10 to the minus 8 molar hydronium. Okay, and so we're getting stronger. We're 10 times more basic than water. What if we went up to pH 9? This would be 10 to the minus 5 molar hydroxide, which, right, if we had 10 to the minus 5, we would be to add to 14, this would be 10 to the minus 9. I'm sorry, I have that backwards. This would be 10 to the minus 9. This would be 10 to the minus 5. Okay, so now we're getting to very much stronger hydroxide solutions. This would be like when we mix baking soda with water. Now, of course, you can choose how much baking soda to put into water, but baking soda is kind of a weak base. All right, go up to pH 10. If you ever, this would be 10 to the minus 4 molar, so this is 1,000 times. 1,000 times stronger than the natural water. This concentration, if you've ever bought it off the shelf because you were sick, like you needed to throw up, they sell this. It's kind of like to help settle your stomach. It's milk of magnesia. Okay, it's a sort of a stronger basic solution, and you would consume it because maybe you had too much acid in your stomach or you wanted to neutralize that. Okay, what about pH 11? This would be 10 to the minus 3 molar hydroxide. Okay, at pH 11, cleaning stuff, so like ammonia. Ammonia is kind of it's considered a weak base, and we talked about why it's considered a weak base, but if the concentration they put in, like, let's say Windex or something, would make it very close to about 10 to the minus 3 molar. So this helps you clean stuff off windows and things. All right, pH 12, there are several soaps in this range. That would be a 10 to the minus 2 molar hydroxide. So now we're getting into sort of a strong base. You'll find a lot of strong cleaning agents are basic in nature. When you get up to pH 13, now we're getting to the danger zone. This is like 10 to the minus 1 molar. Remember, 10 to the minus 1 molar hydronium was similar to stomach acid. Well, 10 to the minus 1 molar hydroxide will be about as dangerous as stomach acid, but in the other direction, and this is like bleach. Bleach has a concentration close to about 10 to the minus 1 molar. And if you kept going to like pH 14, this is super strong. This is like something we would use in the lab. All right, this is like 1 molar hydroxide, or 10 to the 0. Drain cleaner, stuff you use to unclog your drain, like Drano, has really nasty, really strong base hydroxide concentration in there, and it's dangerous, right? Every year people get admitted to the hospital because they usually it's young children who accidentally drink the Drano and they get very hurt. Okay, but that's the pH scale. It's literally, they're talking about factors of 10. This is known as a logarithmic scale. Okay, factors of 10. Every time you go up 10 times stronger, you get one rung higher on the ladder. And there is actually an equation we can use to calculate this. It's the pH. If you wanted to actually calculate the pH of a solution, you would take the negative log. This is a function on your calculator. It's technically log in base 10 of the concentration of the hydronium ions. Okay, it's based on the hydronium, not on the hydroxide. We can figure out the hydroxide concentration by making them add up to 10 to the minus 14. Okay, but this is generally speaking how you do it. And if you wanted to calculate the actual pH, you can reverse that, which is basically raise both sides to the power of 10, and that'll clear the log. Okie doke. So that is the pH scale.